So what am I about to talk about? Well, how stars are formed, and I guess there's a bunch of questions we might like to ask that are similar to the questions that tabloid journalists might ask. What is forming? Where is it forming? How does it form? And why do stars form at all? And I'll address each one of those questions as we go through the evening. But I guess the most important one to start with is, what are we creating? What is a star? And our nearest star, of course, is this one, taken at a nearby World Heritage Site, this image. The sun's been that way for about 4.5 billion years, and is going to be pretty much the same for another 4.5. It's about middle-aged now, but 4.5 billion years ago it formed, in astronomical terms, in practically a blink of an eye. This image was taken on the summer solstice in 2008, and the most impressive thing about this image by far is there's not one hippie or druid to be seen. So let's talk about the properties of the sun. The sun's a fairly typical star. So let's talk about how much it weighs. It weighs 1 billion tons, which is a lot of mass. So let's try and put that into more of a context. In terms of the solar system, the biggest planet in the solar system is Jupiter, and the sun weighs almost exactly 1,000 times as much as Jupiter does. The Earth, well, the sun weighs about 330,000 times. The sun weighs 330,000 times as much as the Earth does. I've exaggerated the Earth's size in this image. It should really be about that big compared to Jupiter. How big is the sun? Well, 700,000 kilometres in radius, 140,000 kilometres in diameter. And let's put that in context as well. Well, the Earth has a radius of about 6,400 kilometres. And Jupiter is quite a bit bigger, as you've just seen. In fact, about 10 times bigger than the Earth. So we can take 10 Earths and put it across one Jupiter. And fortuitously, if we take our star, that again is 10 times as big as Jupiter is. So we can put 10 Jupiters across the face of our sun, or 100 Earths. And so 1,000 times Jupiter mass, 10 times Jupiter's radius, and it sits there billion year after billions of years, rotating once every 30 days. And the movie on the left there that you're looking at is an image taken in ultraviolet, where a lot of high energy radiation comes out and is controlled, the material that emits that is controlled by magnetic fields. So you can see loop-like structures in that image of the magnetic field of the sun coming up through the surface, a little bit like bar magnets dotted around the place. The surface of the sun is about 5,500 degrees C, but as you go down in towards the sun, it gets hotter and hotter because there's a lot more mass down there, and a lot of weight and a lot of pressure, and the core temperature is about 10 million degrees centigrade, and at that temperature hydrogen atoms or hydrogen nuclei come together and form helium, and that's the process that powers the sun through these billions of years. But it's not, as we'll see, the process that powered the sun when it was first formed. So that was what's formed, and pretty much a star is a star is a star. Some are big, some are small, but most of them look like that, frankly. Whereabouts do they form? Well, the answer is in molecular clouds. And so let's have a look and see what those things are like. This is an optical image of a galaxy called M83, which is one that's quite similar to our own. It's a little bit smaller, about half our size, but the structure of it, with these spiral arms and a central dense sort of nucleus of stars, is very similar to our own. And you can see red patches dotted throughout the spiral arms there, and it's those red patches where we're seeing newly formed stars. I'll put a size scale on there for convenience, and that says 15,000 parsecs. Now, parsec is a big unit of distance. It's about 3 light years, if you want to talk in light years. But all you need to know is a galaxy is about 10,000 of them across. Okay, and we'll use that unit a bit later on. So a galaxy is 10,000 of those units inside. what we want to do is find regions where stars form that are much closer to us. And one such region, fortunately, is in Orion. It's one of the nearest regions to us that forms all types of stars, both high and low mass stars. So this is an area, observationally, that's very rich, and a lot of telescope time is spent looking in this area, which you can really regard as a stellar nursery where stars are being born and formed. And this is the physics building where I work, the beautiful Sir Basil Spence creation. But above there, at the top, is the constellation of Orion, and of course Orion's a hunter, and of course that looks exactly like a hunter to you and me, doesn't it? I'll draw it on just to, there we go. The star Betelgeuse at the top left-hand side is a red supergiant. The bottom right-hand star is Rigel, which is a blue supergiant. And the bit that I've shaded there is where the star formation is going on in Orion's belt. This is an object called M42, the Orion Nebula. So let's imagine we had a much bigger telescope on the roof of the physics department than we actually have, and we take a picture of it. This is a computer we use. It's a supercomputer, has 2,000 processing units within inside it. Okay, so your computer at home probably has 2, and this has 2,000. It has 4 terabytes of memory in it, 70 terabytes of disk space, and the main bottom line figure is it can do 20,000 billion calculations every second. And we use that to model the star formation process. This is not a calculation that I did, but a colleague of mine, Matthew, and it was too pretty to leave out. So this is a molecular cloud undergoing that process of fragmentation and collapse to produce newly formed stars. You can see it's a chaotic process. It's very three-dimensional. There's a lot of movement, a lot of kinetic energy, and eventually you'll start to see points forming in there, white dots, and those are your protostars being formed out of the dust and gas in the calculation. All right? The timescale here is on the order of a few 100,000 years.